All right, chapter 15, we're going to talk about chemical equilibrium. And this is a good step forward from what we've been talking about with rates. Equilibrium is dealing with rates, and applying what we've learned in rates, we're going to carry over into equilibrium. So what the heck is chemical equilibrium? Well, equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. So you can see here we have N2O4, and in the reaction it's going to 2 moles of NO2. That reaction can happen forwards and in reverse. And when a reaction happens forwards and in reverse and their rates remain constant, we're at equilibrium. So let's look at this example a little bit more. We have NO2, we have N2O4. And the reason that NO2 is squared, remember, is that we have 2 moles of NO2. So what's going to happen is this reaction takes place, the concentrations are going to level off. And when the concentrations level off, that means we are at equilibrium. And again, when we're at equilibrium, that means our forward and reverse reactions are occurring at the same rate. So just another picture here. We have N2O4, NO2. Once equilibrium is achieved, the rates are going to remain constant. They're not going to be the same, they're just going to be constant. So what's this look like? We're going to use our double arrow to show that a chemical reaction is at equilibrium. We're going to have a forward arrow and a backwards arrow all at the same time to show that we have achieved chemical equilibrium. Now, what we can do is when we know something is in equilibrium, we can use it and we can apply it to solve for the equilibrium constant. So this equilibrium constant is going to be able to help us calculate rates, and it's another way that we can calculate the rates, but actually using concentrations, we're going to calculate Kc. So if we review here, our forward reaction, we have 1 mole of N2O4 going to 2 moles of NO2. Our rate law then, based on our reactants, is going to be K times N2O4. If we do the reverse reaction, now we have 2 moles of NO2 going to 1 mole of N2O4, and our rate law is going to be K times NO2 squared. All stuff we've done in chapter 14. Now, what we can do is, if we look at an equilibrium, we can take Kf over Kr, which is, what we have here, our final over the reactants, vice versa. And we can rewrite this to get an equilibrium equation. And what we're going to do is Keq, or what we will call Kc, because it's the equilibrium constant, really is equal to the products over the reactants. So if you take the products, and in this case our products were NO2, so we're going to take our rate for our products, which is NO2 squared, divided by the rate for our reactants, the concentration of N2O4, and you get NO2 squared over N2O4. So it's really the rate of your products divided by the rate of your reactants. And we can classify that as if Keq is equilibrium, you'll see it as Kc, which is just equilibrium constant. So that's what we're working on, is Kc. So in general, if we have a reaction here, the AA plus BB yields CC plus DD. The little letters representing the coefficients, the larger letters representing the actual concentrations of compounds. We can take the concentration of our products to the exponent of the coefficient divided by the concentration of our reactants, again, to the exponent of our coefficients. And that is how we're going to express Kc. Now, with gases, remember, we can use pressure instead of concentration. So if we're dealing with a wide variety of gases, we can take the pressure instead of the concentration of the solution. So when we solve for Kp, Kp is going to deal with pressure, and we can take the concentration or pressure of the gases. So remember, pressure and concentration are equivalent to one another, or proportional. So we can take either concentration or pressure when we're studying a gas. So Kc is really the products, the rate of the products over the rate of the reactants, and we can take pressure to do that. However, we can rearrange the pressure equation to get the following equation. Kp is equal to Kc times RT to the change in N. Now the change in N is equal to the moles of gas minus the moles of reactant, or sorry, the moles of gaseous product minus the moles of gaseous reactant. And the key there is moles of gas. You're going to count your moles of product minus your moles of reactants, but you're only going to count your moles of gas. You're not going to be concerned with liquids and solids when you're looking for Kp. So R again is our gas constant, which we've talked about 100 times. T, make sure yours is in Kelvin. You'll be given Kc if you need to solve for Kp. So Kp is second equation for Kp. So if we do a real-life scenario here with real-life data, you don't have to worry about copying this data down. But if you look in the last right-hand column, you can see Kc, 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 Kc all the way down. That's our equilibrium constant. So if you look in the right-hand column here, Kc, our Kc value doesn't change. What this is showing is it doesn't matter what our initial concentration of either of these substances are, our Kc value is going to hold the same, showing that the ratio holds the same, or our equilibrium constant is going to be the same no matter what our concentration of reactants and products when we start the reaction. So just something interesting to note there. And this is the data from the experiment, again showing that the rates when we achieve equilibrium are going to level off. And here they just happen to level off at pretty close to the same concentration. Here's an example, another example, except when you were using three substances, you can see that equilibrium is achieved when all three concentrations stay constant. So they're not the same, but they're constant. So just something to note there. Last thing we're going to talk about here with K, what if K is greater than 1? If you solve for Kc and Kc is greater than 1, that means the reaction is product favored. So if K is greater than 1, it's product favored. If K is less than 1, it's going to be reactant favored. So if Kc is less than 1, it's reactant favored. If Kc is greater than 1, it is product favored. So just a little idea here of what we can do. And then that is about it, what we want to talk about. So what we're going to continue in section 15.2 is what happens if we have two steps. What if we have a net reaction of two or more steps? How do we figure out the equilibrium constant for each step, and then how do we figure it out for the overall reaction? So in 15.1, we had a general idea of what Kc is, our equilibrium constant. We can solve for that, which is Kc. Remember, that's the rate of your products divided by the rate of your reactants. We also can solve for Kp based on the concentration of the gases or the pressure of the gases. And then remember that when we are talking about equilibrium constants, if K is greater than 1, it favors the products. If it's less than 1, it favors the reactants. That's kind of the end of section 15.1. If you have any questions, you are free to come in and talk. Other than that, that'll be it.